Hello and welcome. In this video, we're going to take a look at the solutions for Unit 6, Lesson 1 on integer exponents homework. Please remember to pause and rewind the video as necessary. Let's take a look. Write each of the following exponential expressions without the use of exponents such as we did in lesson exercise 1. Well, if you look in part A, we're breaking this down into factors or multiples of 2. So if we look, what we're given is we're given 2 to the first power, which is 2. And we can see when we multiply by 2, that's 2 to 2 squared is 2 times itself twice. We get 4. 2 cubed would be, of course, 2 times 2 times 2, which is 8. Now you can see when we're going in one direction, we're multiplying by 2, right? In the other direction, we're dividing by 2. So to go the other way, we're dividing by 2. 8 divided by 2 is 4, right? 4 divided by 2 is 2. That means 2 to the first power would be 2 divided by 2, which is 1. Anything to the 0 power is 1. 2 to the first power, again, if we take 1 divided by 2, that would be 1/2. 1 over 2 to the first power, which is 1/2. If we divide it by 2 again, that is 1/2 of 1/2, which is essentially 1/4. 1/2 of 1/2 is 1/4. And if we divide by 2 again, we have 1/2 of 1/4, which is 1/8. In part B, we're doing the exact same exercise, but we're doing this with 5 as the base. Starting off with 5 to the first power, we get 5. 5 to the second power is 25. 5 to the third power would be 5 times itself 3 times. 5 times 5 times 5 would be 125. Now, if we go the other way, we're dividing by 5. So if I take 5 and I divide it by 5, all right, go the other way, we're talking about 1 because, again, anything to the 0 power is 1. If we divide by 5 again, we're talking about 1 over 5, or 1/5. So 1 divided by 5 would be 1/5. If we divide by 5 again, 1/5 divided by 1/5 would be 1/5 of a fifth, and 1/5 of a fifth would be 1/25. And if we take 1/25 and we divide that by 5 again, we're talking about 1/5 of a 25th. We're talking about 1/125th. In exercise 2, we're going to go the other way around. For each of the following, determine the integer value of n that satisfies the equation. The first one is done for you. Let's take a look at what was done in the first equation. 2 to the power of n equals 1 over 8. Well, notice we just rewrote 8 as 2 to the third power. Then we wrote the positive exponent as a negative exponent by bringing it up. And then if you notice, if we have 2 to the n power equals 2 to the negative 3 power, that must mean n has to equal negative 3. So in other words, what are we going to do for this one? We are going to get the bases to be the same. So when the bases are the same on both sides, that's what we want to do. We want to get the bases to be the same on both sides, and that's what we did. We have a base of 2. We wanted to rewrite this so that we get another base of 2. So we have 2 to the n equals 2 to the negative 3. Therefore, n has to equal that missing negative 3. So we're going to do that same pattern. Well, 4 to the n, you can write 16 as 4 to the second power. That means n has to equal 2. In C, first thing we're going to do is we're going to rewrite this as a negative exponent. So this is the same thing as, well, actually, I don't need to write it as a negative exponent first. I can write it to something as a power of 3. 1 over 81 is actually 1 over 3 to the 4th power. But I can now rewrite this as 3 to the n equals 3 to the negative 4. So I can rewrite a positive exponent as a negative 1 by taking its reciprocal. And then you can see if 3 to the n equals 3 to the negative 4, then n must equal negative 4. Seven to the n equals 1. Well, remember, anything to the 1 power, or anything that gets you 1 is anything to the 0 power. So I want to make sure we have a base of 7, right? So I'm going to rewrite 1 as 7 to the 0 power. Because remember, 0 to the power equals 1. Why am I writing 7 to the 0 power? Because I want the bases to be the same, remember? And if the bases are the same, and n to the 7 to the n, equals 7 to the 0, then n must equal 0. I'm going to, in letter E, write 25 as 5 to something power. So this would be 1 over 5 squared. And then I can rewrite this as 5 to the n equals 5 to the negative 2, because I can rewrite this as a negative exponent. And you can see if 5 to the n equals 5 to the negative 2, then n must equal negative 2. In letter F, 10 to the n equals 1 over 10,000. Well, 10,000, this is really easy because 10,000 has 4 zeros. So that means that 10,000 is actually 10 to the 4th power. Well, we'll rewrite this as, rewrite that negative exponent, that fractional 1 over 10 to the 4th as a negative exponent, 10 to the negative 4. And so if 10 to the n equals 10 to the negative 4, then n has to equal, in this case, negative 4. Letter G is pretty much the same as letter D. 13 to the n power is going to be 13 to the 0 power. We're writing this as 13 to the 0 power so that it can equal 1. And if 13 to the n equals 13 to the 0, then n must equal 0. And in letter H, 2 to the n equals 2 to the 32. Well, it turns out that 32 is actually 2 times 2 times 2 times 2 times 2, which is 2 to the 5th power. So we can write this 2 to the n, rewrite this as 2 to the negative 5th power. And if 2 to the n equals 2 to the negative 5th power, then that must mean n is equal to negative 5. In exercise 3, we're going to use the addition property of exponents to simplify each expression, then find a numerical answer without using a calculator. Well, what is this addition property of exponents? Addition property of exponents says that if we have x to the a power times x to the b power, we're going to end up adding those. If the bases are the same, we end up adding them, and it's x to the a plus b. So let's use that property here. So this, we have the same base. We're going to take all those exponents, we're going to add them together. So this is really 2 to the negative 5 plus 3 plus 4, which is actually negative 5 plus 3 is 2. as negative 2, excuse me. Plus 4 is positive 2. And 2 squared, of course, is 4. Letter B, this would be 5 to the 3 plus 7 plus negative 10. All of those add up to 0, and 5 to the 0 power is equal to 1. Letter C, we have 10 to the 3 plus negative 7 plus 2. This would be 10 to the 3 plus negative 7 is negative 4. Negative 4 plus 2 is negative 2. Well, 10 to the negative 2 is 1 over 10 to the positive 2, which is 1 over 100. In number 4, we're going to use the product property of exponents. So the addition property of exponents, we add the exponents if we have same base. So same base add exponents. That's the addition property. The product property, I kind of refer this as a power to a power rule. And what it basically states is, if I have x to the a power raised to the b power, this becomes x to the a times b. In other words, power to a power, we multiply the exponents. Let's try this. For letter A, this would be 2 to the 3 times 4, which would be 2 to the 12. And it's okay to leave it like this and not get, we do not need a final numerical answer. So just express it as a simplified exponential expression, as 2 to something power, 3 to the something power, or in this case, 5 to the something power. So in letter B, this would be 3 to the negative 2 times 2, which would be 3 to the negative 4, which is one way to write it, or 1 over 3 to the positive 4. That's the other way to write it. Make sure you're comfortable expressing it both ways. And in letter C, we're going to go 5 to the 2 times negative 4 times negative 2. Well, 2 times 4 is negative 8. Negative 8 times 2 is positive 16. So this is actually 5 to the positive 16 power. Big number. In part 5, the exponential expression 1/8 to the 4th power is equivalent to which of the following? Well, let's actually break this down. 1/8 to the 4th power is actually 1/8 times 1/8 times 1/8 times 1/8. Now, each of these, I'm going to put these into 4 groups. This group right here would be 1/2 times 1/2 times 1/2, because 2 times 2 times 2 is 8, times this group right here would be 1/2 times 1/2 times 1/2. This group here would be 1/2 times 1/2 times 1/2. And that final group would be 1/2 times 1/2 times 1/2. And if we count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, this is actually 1 over 8 to the 4th power is actually 1 over 2 to the 12th power, which is 2 to the negative 12. Part 6, how can you use the fact that 25 squared equals 625 to show that 5 to the negative 4 equals 1 over 625. Well, start with 5 to the negative 4. 5 to the negative 4 is really 1 over 5 to the positive 4. Now I can rewrite that. That would be 1 over 5 times 5 times 5 times 5, right? 5 times itself 4 times. But if I group these, 5 times 5 is 25, isn't it? So this is also the same as 1 over 25 times 25. And what did we just tell you? 25 squared is 625. Number 7, we've extended the two fundamental exponent properties to negative as well as positive integers. What would happen if we extended the product exponent property to fractional exponents like 1/2? Let's play around with the idea. Part A, use the product property of exponents to justify that 9 to the 1/2 power squared equals 9. Well, let's try this. 9 to the 1/2 power squared. Well, that's the same as 9 to the 1/2 times 2. Remember, we multiply product to a product, which is the same as 9 to the 1 power, which is the same as 9. Pretty easy to verify that. And what other number can you square that results in 9? Well, of course, 3. 3 squared equals 9. I hope you found that helpful. Again, please pause or rewind the video as necessary. Thank you.